So good afternoon, my name is Stephanie and I will talk about two methodologies to improve the use of satellite data over land, snow and sea ice in the HARMONIE-AROME forecast system. So as it was mentioned earlier a couple of times in the polar region, with regard to satellite observation, conventional are quite sparse. And in order to use satellite observation in NWP, it is necessary to have a model equivalent that is close enough to the observation. And that's very often the reason why we are not using this observation in an optimal way. And if I give an example, here is on the right side, you have two maps of satellite observation, and on the left side, you have the available against active observation, and you can really see that we are underusing this observation, especially when they are sensitive to the surface. So here we'll talk about the first methodology, which consists in improving the radiance simulation. So we're going to work in the with the level 1 product in order to be able to assimilate more observation. So here is the methodology used by Fatima Karbou, and it is about retrieving the surface information from one channel on the instrument and then allocate this information to the adjacent channels. So here we'll talk about the surface emissivity, and I will give you two examples about the AMSU instrument and MHS instrument. So here, very briefly, so on the left side you have the maps of two maps of surface emissivity, and on the right side is the difference between the radiance simulation and the radiance observation. So in the first line is what we are presently using in the HARMONIE-AROME, so the default surface emissivity, which is a classification-based emissivity scheme. And we can see that if we are using the scheme on the right side, we are doing quite large error on the brightness temperature simulation, which can be over 4 Kelvin. So for example, for if we simulate channel 4 using this surface emissivity, which means that at the end, almost 95% of the observation will not go through the quality check and will not benefit to the atmospheric analysis. But then, if instead of using this default emissivity, we are using this retrieved emissivity from a channel on the same platform, so for example, from channel 3 of AMSU-A, we can see that the difference between the radiance observation and simulation is quite reduced. And we will allow more observation to pass the quality check and then to contribute to the atmospheric analysis. So same if we are checking about the emissivity about on sea surface, it's the purple. So as you can see in the first line in the control, so in the default emissivity is static over sea ice. But then if we are using the retrieval, we can capture better the variability and then the impact on the difference between simulation and observation is the difference is quite reduced, and then we will be able to better constrain the analysis. So if I check the impact on the forecast and the analysis, here is some quick statistics versus the radio sound that we have on the domain. And the curves on the left is the bias, on the right is the RMSE, and we can see that the control is in purple, that we are able to reduce the bias in the low level of the atmosphere. So that was the first methodology. Then I will talk about another methodology that we've tested in Norway, and I will present the result on behalf of Yuri Batrak. In this methodology, you assimilate a level 2 and level 3 satellite product within the surface model. So here he's using the near real-time SeaIce product assimilation into surface. So the SeaIce in AROME Arctic, it is represented by a very simplified scheme, which is called SeaIce. And it has been noted that a large bias of the ice surface temperature, especially in snow-free configuration, describe a large bias. So he was wondering if data assimilation could compensate for this deficiencies. And obviously, over SeaIce, we don't have we don't have any near real-time in situ observation available for his experiment. So the solution he suggests was to assimilate this near real-time SeaIce product. And for that, he used a bias-aware Anton-Kalman filter flavor to account for this warm bias, especially over snow-free identified size pixel. And on top of that, he applied, to have a stronger impact, he applied incremental bias correction during the forecast. So just note that also in the state vector, it was include the snow and the ice temperature. So that's the main result he got. On the top left, you have the map of sea ice concentration and also the location of observation. And what he saw is that it gets mainly positive impact on the analyze and the forecast. So in particularly, he noted an overall reduction of the RMSE versus the T2 matter, except on some close, near to the ice edge, which we can see some degraded score. But on overall, when we compare to another satellite product, he noticed a large positive impact, as you can see on the right plots, the black curves against the orange. So in conclusion, as it was mentioned, the polar region benefits from a high density coverage of satellite observation, but we are still limited in terms of usage, especially over complex surface. And this can be due to the uncertainties in the surface emissivity and temperature. So I've been presented two methodologies to improve the use of this data in the polar region. And the first one was about retrieving the surface emissivity from a window channel and allocate this information to sounding channel in order to better simulate these radiants and increase the amount of assimilated data, which will have in return an impact on the forecast here. And I was also talking about the assimilation of this near real-time level 3 satellite product of SeaIce. And it was noted that we got positive impact on overall. And it was also noted that the effect was rather short, it was not propagated very well in the forecast. And then also there could be also some issue regarding to the timeliness of the satellite product that can be a heavy limit for operationalization. So you can find more details regarding this study in the article mentioned here. So thank you for your attention.
Very good. Any questions for Stephanie? Yes, there's one.
So, thanks. The radiance are the surface radiance. So you have, they are derived with correction for the atmospheric influence. So
We are retrieving the emissivity from
Okay.
from channel 3, but which is really sensitive to the surface, and then we allocate that to the sounding channels.
Okay.
Yes, that was convenient.
Yeah. So I have a question about the assimilation. Now, you showed a positive impact when you assimilated the radiances
Yes.
at low level. Surely that would be affected by the complexity of the stratification, you know, like it might be really big in some areas, you know, highly stratified atmosphere and less stratified in others. So maybe there'd be more information about the validation if you did it more regionally or regime dependent. What do you think about that?
I don't know. It's, I don't know. I will think about it.
Okay, good. Thank you again, Stephanie.